In this video, I want to talk about the logistic function. And it's a very useful function which crops up in a lot of areas. It shows up in economics, statistics, biology, physics, and for example in medicine, it's my understanding can be used to study the growth of a tumor, the growth rates of a tumor rather. And the way I want to use it is as a model to predict the growth of an epidemic throughout a population. That's how I'm going to use it. But the logistic function was named around 1845 by looks like a Frenchman, Pierre Verhulst, I believe is his name, Verhulst. And it results in a S-shaped curve, sometimes called a sigmoid. And so here's an example of a logistic function. And there are two asymptotes, horizontal asymptotes. So in a logistic function, as you approach the right-hand limit, the right-hand limit goes to an upper limit number. And as x goes to minus infinity, it approaches a lower bound. So it's bound between these two values here. Kind of looks like an inverse tangent or something. or maybe a hyperbolic tangent function might look like this. But anyway, so I want to study this, and like I said, the model I want to use is for spread of an epidemic. So I'm going to erase this and write out the problem that I want us to study. Here's the model I want us to look at. Alright, so bear with me here. The rate at which people in a population with a disease is growing, or grows, varies jointly to the number of contagious, to the number who are contagious, and to the number who have yet to get the disease. Alright, so I'll explain this joint variation here in a moment, but to make this work the way I want to, I have to really simplify the assumptions. And so I have a couple of assumptions here. Everyone can get the disease, alright? And no one dies from it. And once you get it, you're contagious. Now, realistically, a disease, if it kills you, then you can no longer pass the disease along. And if you don't die from a disease, at some point, presumably you're cured and you're no longer contagious. And so these assumptions are not terribly realistic, but to build these realistic assumptions into this problem is going to complicate it quite a bit, I think. So keeping this simple, this being an introductory course to differential equations, let's kind of keep it fairly simple here. Okay, so what does this mean here? It varies jointly. Well, you probably somewhere in your past in an algebra class you studied variations. You know, direct variation, inverse variation, joint variation. Joint variation means a product of two or more terms. And so let's suppose that y of t represents the number of people with a disease, at time t. And then, well, how many people don't have the disease? So if I'm working with proportions here, then if 1 equals 100% of the population, then who does not have the disease? 1 minus y of t would be the number without the disease at time t. In other words, 100% minus the number who have the disease. So if 40% have the disease right now, then 1 minus 40% is 60% do not have the disease. And probably I should substitute the word proportion here rather than number. Proportionate. Probably be a little more accurate to say that. Okay. So yeah, as you can see, the assumptions, the language is it's all very sensitive. You know, what do we assume and how we express our language. So we got to be kind of careful about all this. All right, so what would happen then? The rate at which the people is increasing with the disease would be dy dt. So dy dt, or y prime if you will, is equal to k times y times 1 minus y. So in a proportion, or a joint proportion, we need a constant of proportionality. We just can't say the derivative is equal to y times 1 minus y. We need a number in here to allow us to equalize it. And we'll have to calculate this number. Here are the number of people, the proportion of the people with the disease, and here are the ones without the disease. So the joint proportion means I'm going to multiply these together, and then I need this constant k. So here is the differential equation model of the logistic function. That's what the derivative looks like. And then from here we're going to figure out what that function is. That's kind of fun to derive it. But just to, does this make some sense? Well, think about this. If I were to graph this, here is the rate of change, in other words, the rate at which people are getting the disease. And here is y, 0 to 1. So if no one has the disease, then there's no one to pass it to. So the rate of growth is 0. If everybody has contracted the disease, then no one else is getting the disease. The rate of change is 0. What happens in between? People are getting the disease. And it starts off down here. Down here is a low rate at which people are getting disease because there are very few people who have it. So let's say 10% of the population have the disease, then that's how fast it's spreading. At some point, it maxes out and then starts to diminish. And then eventually there are fewer people left to get the disease, and so the rate of growth drops down. But at some point, also, it's going to peak out, and the fastest rate of growth. So I hope that made some sense. I'm going to now solve this differential equation, so I need to do some erasing. So recopy the differential equation up here, and I'm going to separate the variables. It is a separable equation, and we're going to have dy over y parentheses 1 minus y is equal to dt. So k dt rather. So I left the k, I divided by y times 1 minus y, I multiplied by dt, and now we can integrate both sides. So this is a real classic integration by parts problem, and let's just go through that technique real quick here. The idea is to, it's kind of like our problem with the free fall we just did. I'm going to take this fraction and split it up into two fractions, the sum of two fractions. And then if I multiply by my common denominator, y, 1 minus y, then we have 1 equals to a parentheses 1 minus y plus b times y. So you'll, if you're rusty at this partial fraction stuff, you'll appreciate this later when we get into differential operators. Okay, we'll see this a bit. All right, so what do? Let's suppose that y was equal to 0. And if I plug that in, I have 1 equals to a plus 0 times b. So a equals to 1. And then if y was equal to 1, and I plug it in, this will be 0. So I have 1 equals to 0 plus b. So 1 equals to b. So a and b are both 1 in this case, which means I can rewrite this as, let me do some erasing. Okay, so I split up the fraction using partial fractions, and now I can integrate these separately. This is a logarithm, natural log of y, absolute value. And then this integral, I get a natural log, but the minus gives me a negative natural log, absolute value 1 minus y. So take this derivative, the negatives will cancel, and we'll have this plus sign. That equals to kt plus constant. So at this point we can combine our logarithms. So natural log, absolute value y over 1 minus y. And I don't think I really need to worry about the absolute value because y is positive. 1 minus y is positive, so I really don't have to worry about that. Equals kt plus c. And then now what? We want to eliminate the logarithm, so I'll make both sides an exponent of e. And let me go to the top here. So I canceled the logarithm with the e. And on the right side, we've seen this before. E to the kt plus c is e to the kt times e to the c. And if I rename e to the c as a constant c, it's c e to the kt. So, finally, I want to solve for y, my function. So I'm going to multiply both sides by 1 minus y. This gives me y on the left, and then this times 1 minus y will be c e to the kt, 1 minus y. And let's multiply that out. Minus c e to the kt y. And now I'm going to bring this to the left. I hope this is all starting to look kind of routine. At least it looks somewhat like our free fall problem through the atmosphere. Except this is a lot cleaner looking. Okay. So I have this term over here. I'm going to factor out y. That'll give me 1 plus c times e to the kt, and then I'll divide in order to isolate y. So almost done with this. Y parentheses 1 plus c e to the kt is c e to the kt. So I'm going to divide by this term. E to the kt over 1 plus c e to the kt. And then I have one more finesse here. I'm going to, here I have two exponential terms, e to the kt's. If I multiply top and bottom by e to the negative kt, then we'll have it a little bit simpler. We'll have just one exponential term. So I'm going to rewrite that up here. Okay, so what happened is, if I multiply this through here, the e's cancel, I have c. And down here, this term, the e's cancel, I'm left with c. And then plus e to the minus kt. So here we are. Here's kind of the basic model on that, based on the assumptions I made. So that will result in a sigmoid or S-shaped curve. And what I want to do with this, I want to go on to the next video and work an actual problem and with this type of model.